Hello everyone, my name is Ashutosh and I am your teaching assistant for NPTEL's Fiber Optic Communication Technology that is being taught by Professor Deepa Venkitesh. In this week, what we have evaluated is the performance metrics. By performance metric, the first term that we looked at was the bit error rate. Bit error rate is the intuitive understanding for bit error rate comes from how many wrong bits have been decoded when a certain number of bits were transmitted. But Professor Deepa had noted that this is a statistical quantity and should be treated as such. Then we looked at receiver sensitivity as to what is the minimum amount of power, what is the bit error rate, how is the quality factor Q related with the bit error rate, how is the quality factor Q related with the signal to noise ratio, and then we looked at the quantum limit of photo detection. After that, we looked at the amplifier, some concepts of the amplifier. Now, amplifier are widely regarded as the reason for the ubiquitous deployment of fiber is because of the ability to boost the signal in all the channels. So, like classical infrastructure, when you have an electrical signal, you would need one amplifier for each channel. Like if you have 3 channels, you would need 3 separate amplifiers. But if the same thing you have in an optical domain and you have 3 separate channels which are spaced in the frequency, the entire thing can just be boosted by a RPM dot fiber amplifier. There are other class of amplifiers as well, such as Raman amplifier and semiconductor amplifier, but we will not be looking at that. Now we looked at the optical amplifiers. We looked at the 3R concepts where reshaping, retiming, which is done in the electrical domain, and reamplification, what our optical amplifier is going to do. Then we looked at the gain in the saturated and the unsaturated regime. Then there's some important concepts such as what is the bandwidth of the gain, and we would want the gain to be as flat as possible. We looked at the noise figure, that is the noise added by these optical amplifiers, their polarization dependence, their crosstalk, pumping efficiency. And then we looked at the energy level diagram of EDFAS itself. We saw that there was energy level corresponding to 980 nanometer pump and 1480 nanometer pump, and both of these are commercially available. And because the ideal condition is that for the entire band of operation we would have the gain as a flat gain, however that is not possible, so we have to flatten the gain spectrum. Then we looked at signal saturation as input saturation, output saturation, power, signal to noise ratio and optical signal to noise ratio, the AAC and signal beat frequencies. Now noise figures and how the SNR is degraded after addition of each amplifier. Now some of the common criteria is that for optical communication we would want our bit error rate to be less than 10 raised to the power 9, 10 raised to the power minus 9. Receiver sensitivity we usually deal in terms of average power, so minimum average power for a specific bit error rate. Now we had seen that bit error rates, there is a probability of incorrect error detection. That just means that probability of detecting a 0 or a 1 when the other bit was sent, which can be expressed in this way. And this we saw how it can be related to the threshold current and the noise in the system, as I1 is the threshold current for high logic level or logic level 1, I naught is for the low logic level, ID is the decision threshold. We also looked at how this can be optimized given that the noise in the system is short limited, is thermal limited, and if it is a combination of both. After that we looked at quality factor. Quality factor is a parameter that can be easily ascertained and it can help us determine what is the standard of the link. Then we saw the relationship between quality factor and the bit error rate, which was given by the error function. So if the quality factor is of 6, the bit error rate is 10 raised to the power minus 9, and if the quality factor is 7, the bit error rate is 10 raised to the power minus 12. Then we looked at receiver sensitivity and assuming thermal noise limited operation. Then for thermal noise limited operation, we saw that the SNR is equal to Q square. That is a handy parameter that comes into the picture. And then we also looked at the short noise limited operation, where the short noise limited operation where we are in the high power regime, so the number of photon discrete nature of the light itself causes these kind of noises. Now then we looked at some of the, I have just jotted down the different formulas of the related to EDFA, as EDFA is an important concept that might come up again and again in the exams and even in your future deployments. So all of these have just been added here for consideration. Then we saw the noise figure, where noise figure is defined as the SNR input by SNR output, where we see that the SNR input is the original SNR and the SNR output has the output SNR with the gain parameter coming into this. And then we also saw how different cascaded amplifiers and how the noise figure is equivalent is calculated for multiple cascaded amplifiers. So after all of this, I would like to take a look at few of the questions that were there in the assignment. Let us start with the first one. The question is, for a binary modulated system without any waveform distortion, so this eliminates any waveform distortion, if the normalized noise standard deviation with logic 0 and logic 1, so it is given to us sigma 0 is 0.05, sigma 1 is 0.15 milliamps, and it is given as I naught is 0 milliamps, I1 is 1 milliamps, which are the average currents for bit 0 and bit 1. So we have been given bit 0 and bit 1. We have to find the optimum decision threshold. Now, to calculate the optimum decision threshold, we calculate the optimum decision threshold assuming I naught is equal to 0. We know that the I decision threshold is given by sigma naught I1 plus sigma 1 I naught divided by sigma naught plus sigma 1. If we substitute the values from earlier, you know, sigma naught is 0.05 and sigma 1 is 0.15. So let us put the numbers. 0.05 I1 plus 0.15. This is 0. This is 0.05 plus 0.15. This goes away. That leaves me with 0.05 I1 divided by 0.2. Which is 4, which is I1 by 4 milliamps. The unit is milliamps if you are assuming, or let me put it this way, we know that I1 is 1 milliamps, so this is 1 by 4 milliamps. So this gives me the answer for the first question. The first question was find the optimum decision threshold, and assuming the noise figures that have been given in the question, this is the optimum noise threshold. Now the second question is find the QBR and the Q value, find the BR and the Q value. Now the Q value in the system, it can simply be given as Q value is given as ID minus I naught by sigma naught. Or if you do not like this formula, we can always go back to the other formula, which is I1 minus I naught by sigma 1 plus sigma 2. And we just substitute the value. This is 1 milliamps, 0 milliamps, and this would be divided by 0.15 milliamps plus 0.05 milliamps, which is 1 divided by 0.2 milliamps. Milliamps are out of the picture, and then it becomes 5. So we have a quality factor of 5. Now the way to go from quality factor to a bit error rate is given the function which relates Q factor to BER is given by BER is half of complementary error function Q divided by root 2. Now it is just a simple expression where you can substitute the number, and if my calculations are correct, this should come out to be somewhere between 2.8 into 10 raised to the power minus 7, which is slightly higher than our convention set earlier of 10 raised to the power minus 9, or even now we are pushing to 10 raised to the power minus 12. Now let us move on to the next question. Next question is, if the normalized decision threshold of the, so it is saying that let us revisit the normalized decision threshold and what would be the bit error rate. Now without optimal decision, we can, the error rate would be higher. We will see how much, but before we get there, we will see that the ID has been given to us as 0.5, and then we would have to use the actual error function where these are not equal. So this would be error function I1 minus ID by sigma 1 root 2 plus ERFC ID minus I naught by sigma naught root 2, and you can simplify these numbers. And I will leave the expression here for you to arrive at the answer. Let us look at the next question. Now the next question has some set of data that will be useful. Like a direct detection receiver using a pin photodiode has a responsivity of 1 amps per watt, a load resistance of 50 ohm, and a bandwidth of 10 gigahertz. Signal NRZ modulated. We are to neglect the dark current and operate at a temperature of 300 Kelvin. Q is given to us as 6 and 7 for BR values 10 raised to the power minus 7 and 10 raised to the power minus 12. Find the receiver sensitivity for BR of 10 raised to the power minus 12 and 10 raised to the power minus 9 limited by the short noise. Now we have to know that short noise of the detector must remember that the short noise of the detector is due to discrete nature of the photon itself. Now the way we would attempt this question is that we have already seen the relation which relates BER to Q value, and we are to assume no dark current. as it has been given to us in the question. Neglect the dark current noise. We have to assume no dark current noise. Therefore, the current generated due to bit 1 would be given as I1 is equal to 2 receiver power received, where P received is the minimum power faithfully register the bit value. For short noise, sigma naught square for bit value 0 is equal to 0, and sigma 1 square is given by 2q RD bandwidth of the entire detector into 2 P receive. This is sigma short noise, where this is the charge of one electron. This is responsibility. Now let us do this for what are the BR values that we have to consider. We have to consider the Q values of 6 and 7. Let us say for Q is equal to 7, BR is equal to 10 raised to the power minus 12. Now we know that Q is equal to 2 RD P received divided by short noise square plus thermal noise square plus thermal noise. In our case, in this we are assuming only, in this case we are assuming only short noise, hence these sigma 2 is equal to 0. We substitute the value back into the equation, and that should give you something like 57.67 nanowatts. Now similarly you can so I only showed for but the same formula can be substituted for values for Q is equal to 6. Now find the receiver sensitivity for the same BR. Now this time we are limited by the thermal noise. So again we go back to the Q parameter and how is it related by 2 RDP receive by sigma short noise square plus sigma thermal square plus sigma thermal. Now what is the value of sigma thermal? Sigma thermal, first of all, sigma thermal is 4 kBT B by load resistance, where RL is load resistance. We have been given RL is equal to 50 ohm. Now this, we had seen that the short noise, we had in short noise, we had assumed short noise for bit 0 to be 0. However, because this is thermal noise, it will be present for both the cases. So for Q is equal to 6, that is 10 raised to the power minus 9, you would get Q is equal to RD P rec 2 divided by 2 sigma T. 2 would cancel out and you would get RD P rec by sigma T. When you substitute all the values, you should be getting power like 10.92 microwatts. Similarly, Q is equal to 7 has been left as an exercise for the students. Now in this we have to consider both of the short noises and the thermal noise. So we will reuse the formula for which is given by Q is equal to 2 RD P received by sigma short square sigma thermal square under root plus sigma thermal. We will substitute all the values here. And get the result. Now let us look at some other questions from the EDFA side. Here we are given an EDFA operates with 980 pump and is used to amplify 1550 nanometer. So we had these three energy level systems. So this is being pumped and this is my level. This small signal gain is found to be 30 dB for an amplifier input signal minus 30 dB. And the EDFA has a filter bandwidth of 50 GHz. Output saturation power of EDFA is plus 20 dBm. Assume complete inversion, find the optical SNR. So this is assuming input does not have any noise. So we have been given small signal gain. Let me fix that in the current form. Small signal gain is 30 dB. And if I go from dB to linear scale, how do we go from dB to linear scale is equal to 10 log P out by P in. If this is 30, then becomes 30 is equal to log with base 10 P out by P in, which is 10 raised to the power 3. So G is 10 raised to the power 3. My P sig is minus 30 dB. If you do the same math here, you will arrive at 10 raised to the power minus 3 milliwatts. Now, we have been given a filter of we have been given a filter of 50 gigahertz, conversion efficiency of 1. So my optical signal to noise, noise ratio is simply given by the formula G naught P signal divided by 2 N signal inversion H nu by G naught minus 1 delta F, which will come out to somewhere around 78.10, which is somewhere equal to 18.92 dB. Hence, the optical signal to noise ratio after that again is given by this number. So what has happened is, if my signal in the beginning was very nice like this, what has happened is that the entire thing has been lifted, and I have taken only a section of 50 gigahertz here, but there is some spontaneous noise in this region, and that is contributing to the decrease in the signal to noise ratio, which is shown here. This is being shown here. Now let us look at the next question. Repeat question number 7 if the optical signal to noise ratio is 20 dB when the input OSNR is 10 dB. So we know that OSNR is equal to P sig by Pn, where Pn is the noise. Now we know that Pn is equal to P sig plus Pn, where P sig is the signal power. When input OSNR is 20 dB. Well, let me write this here. We will again go back and reuse our handy formula of OSNR, which is given by G naught P signal divided by G naught in the power of noise by 2 NSP H nu G minus 1 delta. Here in this case would be G naught P signal by G naught P signal by OSNR input plus 2 NSP H nu G naught minus 1 del F. And this, if you substitute all the values, this would come out to be 43.85, which is 10 log 43.85 by 1, which will give you 16.42 dB. Now this was considering G naught, this was considering OSNR of 10. If we have an OSNR in of 10 dB, my OSNR after this would become 9.47 dB. You just have to substitute the value back in there to figure out the correct answer. And let us look at the last question of the assignment, which was fairly interesting. It was slightly comprehensive. A 1.3 micrometer digital receiver is operating at 100 Mbps. Now these are very reasonable numbers. 1.3 is one of the transparency windows in the optical fiber, and 100 Mbps is what we usually work at now with our systems. The internet connection that we get has an effective noise bandwidth of 60 megahertz. A PIN photodiode, which is positive negative with an intrinsic region in between, has negligible dark current and 90% quantum efficiency. The load resistance is 100 ohm and the amplifier noise is 3 dB. Find the receiver sensitivity for a BR of 10 raised to as my apologies, these should have been 10 raised to the power minus, these are 10 raised to the power minus 9 and this is 10 raised to the minus 12. The different two quality factors we have been looking at, considering a thermal noise limited system. Now you will see that we have been given eta as 90%, that is quantum efficiency. As 90% and my wavelength is 1.3 micrometer. Now from that we can easily arrive at the responsivity. RD is given by the fact RD is equal to eta lambda in micrometer divided by 1.24, which is 0.9 into 1.3 divided by 1.24, and this will come out to somewhere like 0.94 amps per watt, or equivalently 0.94 milliamps per milliwatts. Now after I have the responsivity of the photodiode, I can calculate the thermal noise considering the amplified noise figure. Now we have been given noise figure of the amplifier. We consider thermal noise, which is sigma t square is 4 kBt, where k is the Boltzmann's constant, 4 kBt delta f Fn divided by load resistance. Now if you substitute all the values here, you would get something like 1.98 into 10 raised per minus 14 ampere square. Now what is the kind of modulation? Now this is a digital receiver, so we'll assume OK modulation, as it is a digital receiver. By digital it means that this is not coherent, there is no coherent heterodyne or homodyne detection. We assume OK modulation format. And with that, what it affords us the opportunity is to link U square with my SNR. Now let us say we have been given to calculate for two different Q values. We have been given to calculate for two different BR values, 10 raised to the power minus 12 and 10 raised to the power minus 9. So let us take 10 raised to the power minus 9, which again with the error function is proportional to the error function. This would give me Q of 6. Now after I know the Q of 6, I can arrive at my SNR is equal to 36. Now that I have arrived at the SNR, I can just go responsivity times P square average divided by sigma thermal square, and this would give me an average power of around, this is SNR into sigma t square by 0.94. This is something like 8.98 into 10 raised per minus 7 watts, which is minus 30.46 dBm. Similarly, it can be computed for 10 raised per minus 9 BR. Not 10 raised per minus, 10 raised per minus 12 BR. For that, Q value would become 7, and you would arrive at the power regardless. And with this, we have looked at the assignment that was covered in the link performance. From next week, we'll look at the next module that is coming up. Feel free to drop any questions that you have into the forum and I'll try to respond to them. Thank you.